So hi, here I am again. Today's video title is, like super weird. I have a video number 1 and a video number 2 and a video number 3 and a video number 4. But you're like, wait, why is this video number 4.5? You'll see later. But first, before we begin, I have to show you 9 images. 9 images of a Mandelbrot set. No, not exactly a Mandelbrot set. Pretty much slices of a Mandelbrot set in 4D. Basically what you were expecting to see, right? Mandelbrot set. Yeah, I could call that a Mandelbrot set. But today I'm just going to call that Slice 0. But why did this come back again? You know why this is Slice 0? I got out the slice, this is the next slice. And the next one. By the way, this is the shape we're going to be studying most of today. The next one, 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 the next one. There is something here, but it's so small, but here, no matter how far you zoom in, there's nothing. You're like, wait, what is happening? It's just like someone is destroying a Mandelbrot set, right? You'll find out. But if we set this to 0 and look at the slices of this solid in another dimension, this is what we get. Looks like someone is biting the apple, right? Because I'm going to make this go a little slower so you can actually see what happened. Now it should have enough time to process all the images. Nothing is happening. But then Mandelbrot set 4. Destructs itself again. Pretty cool, right? We're going to set this baby to 0. Maybe because I didn't get this right. But let's watch it again, but with this set to 0. Last time I set it to negative 0.07. Doesn't work. What if I try to refresh it? So now I'm going to my video again. This is a little it doesn't always do what I want it to do. I'll try this again. It's running way too fast this time. 0.005 times. good. Now let's try to wait. It's taking a long time to get to -1, which is the first time we'll see something. Once again, it looks like a Mandelbrot forming and destructing itself. But this time in a different dimension. So let's change the CR this time and see what happens. It goes very slowly. Nothing is big enough to see until here. Everything is pretty much the reflection from here. So anyway, let me show you something very. If we set the limit to a very small number, I'll have to change the limit to 156 settings again. I mean limit 500. Get all these sorts of dots. And when we try to run CR again, this is what happens. It's actually pretty weird. Yeah. It's actually pretty weird. This is the first proper dot. I don't know why it will look this weird. And then it appears in the center. Anyway, it does look very weird. I have to pause this. Anyway, we'll reset all this. Let's see. Save all this. Of course, the link has now changed. They're all at the original link. So obviously, it seems like there's a big bump over here. But why? Of course, it's still constructing itself. But those are truly beautiful spirals. It looks like someone has eaten the Mandelbrot set and wants to bring it back. It definitely looks like someone has eaten the Mandelbrot set. And far from here, the bulbs all look different. Now, what should I call this? The Finger Valley? Oh yeah, maybe. Anyway, there are those spirals. And it seems like as we get closer to one of the places between the fingers, those get smaller. Of course, I only did this to the 512th iteration, so it isn't very accurate. And Desmos has a zoom limit. As we get farther from Finger Valley, then the spirals all get. And by the way, these should be spiraling on forever. Just the 512th iteration gets rougher and rougher as we doesn't look as good as we get further and further away from Finger Valley. And they will be spiraling inward forever. That is, if I push this to the infinite iteration. Sadly, Desmos doesn't do that. So most people like it to the 3000th iteration or something. I did it to the 512th iteration. It's just pretty good, far away from Finger Valley. Here we are at the main Finger Hill. There's this sort of weird thing which sticks out. What is it? That's the biggest one. That's the bigger one. And it's basically just a repetition. Now let's look at the whole picture. And over here, by the way, this should be the two bulb, but it doesn't really look like one because the Mandelbrot set is still constructing itself. Looks pretty much like the real Mandelbrot over here. Oh. Looks like the sea. Over here is pretty much the same as this finger place. It's pretty much the same. So we don't want to continue this forever. So we have this little Mandelbrot that isn't as precise because I generated it to the 512th iteration, not the infinity iteration. Anyway, you can see it still forming itself and doesn't look very shaped. Let's see this. There's another little Mandelbrot here. And by the way, when we do it by iterations, they actually form in different ways. The big bulb different from the other. Looks nice. this is easy to zoom in. You just repeat the same thing over and over again. But this is hard. Now it's easy again. 4 folds in 3. 8 folds. Whoa, Mandelbrot. But we are going to continue zooming in. EB. Well, basically, they're going to do the same thing again. That seems weird. It looks 3D. Wait, what is this? One of those fractals I told you about earlier? What's in here? Mandelbrot set. This thing is spiky. Broken inside 2 folds in 3. 4 folds. You can notice that we take shorter time, but it doesn't really go down quickly. 8 folds. 16 folds. 32 folds. Blah blah blah. Oh, good. Whoa. Mandelbrot. That was very close. Crazy. There is a 3D Mandelbrot set, though it actually is pretty boring. That's too boring.
Maybe this is Mandelbrot set back to basics. I need your help though. Can you think of a number?
对，要录视频呢。64 and
So what we're going to try to talk about today is the arithmetic of dynamical sequences. Let's do an example. So here's an example maybe you'll recognize. Let's let f of x be the function, 2x plus 1. And what I mean by iterating something under this function is let's start at a point, say x equals 0. When we plug x equals 0 into this function, we get 1. And then let's keep doing that. So when we plug 1 into the function, we get 2 plus 1, which is 3. When we plug 3 into the function, we get 6 plus 1, which is 7. So you look at the last number, so 15, 31. So maybe I'll do 2 more just for a demonstration here. So 62 plus 1, that's 63. And 126 plus 1, is 127. So this sequence is special. So this sequence, you might recognize that each of these numbers in the sequence are off from a power of 2 by exactly 1. So this is known as the Mersenne sequence. Well, people have heard of the Mersenne sequence because this a famous question that we don't know how to answer is, are there infinitely many prime numbers in this sequence? Since this question is so hard, one easier question we could ask would be, what do the prime divisors of each element of this sequence look like?
That seems like a harder question.
Well, it might be a harder question depending on how specific you want to get. But so what I mean by the prime divisors of elements of the sequence is we have these factors, so each number factors into prime numbers as long as we're ignoring 0 here. So 3 is already prime, 7 is already prime, but 15, this is 3 times 5. 31, that's already prime. 63, well, let's see. So 7 is a prime divisor, and 9 is a divisor, but it's not prime. It's actually 3 times 3 times 7. And 127, let's see, I think that's prime, and so on. Anyway, so this is what I mean by prime divisors. And so instead of asking, okay, do we have infinitely many elements in the sequence which are prime, we could at least ask, as we go along in the sequence, do we get a new prime at each step? So that's the question I'm interested in answering. So here, okay, we don't have any prime divisors, but here, 3 is a prime divisor that never appeared before. Here, 7 is a prime divisor that never appeared before. Here, 5 never appeared. 31 never appeared. But here we run into a problem.
We broke the streak.
No new primes.
Is that bad?
Well, depends on what you're interested in. But if the question is, do we always have a new prime divisor? For the Mersenne sequence, the answer is no, because look at the 6th element doesn't have a new prime divisor. But the interesting fact is, after that, all Mersenne numbers have a new prime divisor.
Every single one.
Every single one.
What happened with 63?
Well, it's just, when you're at the beginning of a sequence, the numbers are so close and there's so many primes happening that it can occur that you sort of fail to have this new prime divisor. And it also matters that this was the 6th element of the sequence, but that's a little bit complicated. So the point is that after that 6th element of the sequence, after 63, we always have the new prime divisors. So this is an interesting thing, and I think the next natural question, once you notice that a sequence like this has some interesting property, is what's special about this sequence? What other sequences have this property? So instead of choosing a function like 2x plus 1 to generate my sequence, what if I chose a non-linear function? So if I had an x squared in there. So let's say I chose x squared plus 1. But we can still start generating these sequences. So if we start with 0, if we plug it into this function, it's going to map to 1 again. But when we plug 1 in, we get 1 plus 1, which is 2. When we plug 2 in, we have 2 squared plus 1, which is 5. We plug 5 in, we have 25 plus 1, which is 26. And when we plug 26 in, I happen to know we end up with 677. So because I'm dealing with an x squared instead of an x here, the sequence gets larger much faster. But still we get this sequence of integers. Still we can ask, when do we start getting new prime divisors? So if we look at what we have here, so notice again, 2 and 5 are already prime. 26 is 2 times 13, and 677 is also prime. And it turns out that for this sequence, it's even better than Mersenne sequence. All numbers after 2 have a new prime divisor. So this is proven that after 2, you always get a new prime divisor in this particular sequence.
You showed me an amazing sequence, then you showed me a more amazing sequence.
Okay, well then get ready. So let's do the same thing, except that there's no reason that we're only talking about positive integers here, right? So let's look instead at something like this and see what happens. So again, we start with 0. 0 maps to negative 1. Negative 1 maps to 1 squared minus 1, which is 0. But we already know where 0 maps. 0 maps to negative 1. And so the sequence we get is completely not interesting.
I think that's cool.
it's because -1 is in the center of the 2 repetition bulb.
Well, it's definitely not going to have this property that we have new prime divisors, at least. So this is bad news, right? As far as this question is concerned, this is a weird sequence. So let's try a different negative number. Let's try, I don't want to try -2, and maybe you can try it and find out why. Let's try instead -3. All right, so let's go. So 0.
You don't want to
0
try
maps to-
-2. You know, I know why. going to start there, and then it's going to be constant at 2.
0 minus 3. Minus 3 maps to 9 minus 3, which is 6. 6 maps to 36 minus 3, 33. 33 maps to something messy that I don't want to calculate. But now, we'll get an infinite sequence again. Instead of having this repetition like we had in the -1 case, we'll get an infinite sequence. And again, the sequence will have new prime divisors at each point in the sequence, every time.
I'm beginning to think this isn't such a special thing anymore.
I know. So, let me tell you, you're sort of right. So, here I'll write down a general fact. If, say, c is an integer, so a whole number or the negative of a whole number, and c is not 0, -1, or -2, mostly because we want to avoid this problem, then every element of the sequence that's generated from x squared plus c has the prime divisor.
So the only exceptions are 0, -1, -2.
This works for x squared, but it works for x squared plus an integer. If you wanted, you could ask this for a fraction c instead of a whole number c. So if c was 1/2, let's say, so if f of x is x squared plus 1/2, well then what starts happening? So 0 maps to 1/2. Now the computation is a little less pleasant, but 1/2 is 1/4 plus 1/2, which is 3/4. 3/4, when we put it into this function, we have 9 over 16 plus 1/2, which I guess is 17 over 16, does that sound right? And so on. So even though we're getting these fractions in the sequence, the denominators are just powers of 2. And so when you try and factor them, the only prime that you get there is 2. So we can still ask the same question about the numerators in the sequence.
So we're just going to ignore them.
Just ignore the denominators. There's not interesting stuff there happening there anyways. So if you ignore the denominators, then we look and we have the sequence 0, 1, 3, 17, and so on. And it turns out that, again, you will have this property. It seems sort of fundamental, and part of the reason why is because I've been hiding an example from you. So maybe one last example of computation that I'll show you is this kind of tricky little thing here, x squared minus 7 over 4. So what does 0 map to? 0 maps to minus 7 over 4, 21 over 16, minus 7 over 16 squared. All of a sudden, everything comes to a stop, because look at our numerators. 0, 7, 7 times 3, so 3 is a new prime divisor there. But here, we don't have a new prime divisor. So there's something different between 1/2 and minus 7/4. For some reason, there's an element in this sequence where the numerator doesn't have a new prime divisor.
And is this the only number, the only fraction that throws the spanner in the works?
We don't know. We don't know. So just to give you a hint of why this is true, so this is the only one that we know of, but we don't know if it's the only time it can possibly happen. So what's really going on behind the scenes here has something to do with a particular set of numbers known as the Mandelbrot set, which I won't go into, but it's this interesting fractal where things go kind of crazy, and it's hard to draw a fractal, so I'll try my best. Thank you.
Not good
So
at drawing
puts this into perspective for you. So this is a picture of the complex numbers, and I'm interested in the numbers that are inside of this set. And let's look at the values of c that we've done this computation for. So 1, we first did x squared plus 1. 1 is over here. We also did minus 1. Minus 1 is over here. We did minus 3, which is well outside of this set. We did 1/2, which is also not inside this set. But minus 7 over 4, it is inside of this set. So minus 7 over 4, it turns out, which is right inside this piece of the Mandelbrot set.
This line of the real numbers there.
That's right.
Seems to run right through a whole swathe of fractions that would be. Aren't there going to be loads of fractions that are going to cause this problem then?
That's a really good point. So you're absolutely right. There's tons and tons of fractions on the real line inside of the Mandelbrot set, but it's not enough, it turns out, to just be inside the Mandelbrot set. You have to be particularly very far inside of the Mandelbrot set. And so this is really saying something special about where the number c can lie inside of the Mandelbrot set.
So if there are other numbers like minus 7 over 4 that are going to throw a spanner in our works, they definitely have to be in here.
That's right. So right away, you get for free that if you take a large enough fraction, say bigger than 1, for example, although you could get closer, for free you get that there will always be new primes in those sequences. But yeah, if we were to look for other examples of where this might occur, they would have to lie inside of the Mandelbrot set, and they would have to lie well inside the Mandelbrot set, actually, it turns out.
But it looks like there are numbers here that would be pretty well inside the Mandelbrot set, or is it a particular...
It's a particular thing. Inside each of these bulbs here that I've drawn sort of half-heartedly, there's a special point. And what might happen, the only reason why this might happen is if your rational number is very, very close to that special point, in a technical way that is hard to formulate. I think at heart people don't believe that there's one beyond.
If it's very close to that special little point, you know what happens. It basically converges to the cycle very fast.
Minus 7 over 4. If I had to make a guess, I would say probably not. But it would certainly be nice to know that for sure.
But why 63 special? Anyways, Mandelbrot, wait, hi, what are you? Completed Mandelbrot. What's the difference between this and this? know how you get that special point? Oh, it depends on the value. For example, the value is 4. I'm taking some number Z in, and then you do it 4 times, and then you take the output, and you set, and there might be multiple solutions, and 4 divisors are 2 and 1. So you do that also for 2 and 1, and you take those in 4 that aren't in 2 or 1. And you number them. So we basically have this picture where 3 is directly overhead of 1, 4 is a little to this side. But in fact, I have almost the decimals for everything. This is what I did last time. The moon moved very slowly, so that's why I did it sort of like this. So I decided that maybe I could use this to make a carotid. Silly. Better. cardioid. This is about where the forebulb is. Wait, let me see the... About at 0. This is next time it returns here. Basically set a variable called the time. Well, like this, that's when it started. But where the 3 bulb is. That's where the 4 bulb is. Look at this wave. Which bulb is this? I do not know. Maybe that is not even a bulb at all. Where the 5 bulb is. There's something must be wrong about this. Why do I have so many things that have 2 on them? Definitely like 3D. Here's it with 5bx. With 6bx. Looks very bxy. With 7bx. With 8bx. Looks Thanks for watching.